the recording?
Yes, we have started the recording.
Okay, should I just begin talking, Jane, or do you want to say
Oh,
something?
no, yeah, first okay, so Terry gave us some history and motivation yesterday. It was so interesting that I look at it today. The more I look at it, more interesting. And today, and he also gave us an outline of what he is going to talk in the next few days. And today is going to start with the variation geometry. Terry, please.
Yes. So variational geometry. Geometry. Why is geometry important? Of course, in our own mathematical educations, after arithmetic and a bit of algebra, well, we go into geometry quite easily. And geometry is so important because of the way the human mind works. Mathematics is a completely abstract subject, as we know, but it's designed to react with things that we understand and we live with, and it's going to be useful. And although some parts don't have much geometry, for example, the theory of prime numbers, many of the concepts in calculus and mathematical modeling do involve some kind of geometry. And it's a miracle of the human mind that our experience with 2- and 3-dimensional, not to mention 1-dimensional geometry, gives us a way to understand and organize many ideas that are far more complicated. For example, you are all mathematicians, and you all know, and you all are perfectly able to imagine a hyperplane in a space of 1,000,000 dimensions. We can't see it, we can't know just what it is, but this is a concept that is quite clear to us, what a hyperplane or what a subspace is, what dimensionality is. And all these ideas of curvature, even though we only see things in 2 and 3 dimensions, we can carry over. So it's very valuable when a subject can be tied to a kind of geometry that is visualized. And of course, as I will explain, that's true with a lot of the classical analysis. It's tied to geometry that was understandable, and that gives it some of its power. But as I tried to explain yesterday, when we come to variational analysis, we have to make a break with some of those ideas in the past. So I will begin today again with some kinds of history. So the first, let's see, I can get rid of this little thing. Okay. So this, to start the history, let's just go to the kind of differential geometry you perhaps learned first in advanced calculus. And even then more in higher forms like the theory of differentiable manifolds. All this kind of mathematics that you could say is basically inspired by physics. And physics is mostly in 2 and 3 dimensions, although we know the models in some ways can be, even infinite dimensional, for example, quantum physics. But we picture things in physics like curves and surfaces. And as we studied in the calculus, we could imagine those are being defined by some sort of equations. And as I explained yesterday, equations are exactly the mathematical workhorse of classical theory. So this is like, this is the kind of geometry associated with equations. But it also could be abstractly, it's like some kind of manifold. So we have some sort of manifold, and we don't have to define what it is here because you all have a good picture of it. But the key to this is geometrically is that you can look at tangents to this kind of set. You pick a point X and you look at tangent vectors to the set. Now let me make clear that when we study calculus and we look like a tangent to a curve or a normal to a curve, often these are made to be vectors of length 1. But for me, this is not the case. So it could be of any length. So I'm looking at all the tangent vectors to this set C. Think of it in your mind maybe as a surface more than just a curve. I look at all the tangent vectors at this point of the surface, and they will form a subspace. Now remember, again, the picture is a little misleading because the picture looks like the tangent cone, the base of the tangent cone is at, the subspace is at X, but actually it's at the origin. the vectors in this tangent space are floating vectors, and we picture them as attached to X, but really they form a subspace. So we have all those tangent things, and they would define actually a hyperplane, which is touches at this point. But then we also look at the normal vectors, and the definition of them, as far as I know, is just through orthogonality. So first of all, so how would you describe a tangent vector? You go to the more basic idea of the tangent vector to a curve. So I'm thinking here in the middle of this slide, I think of a kind of a curve, which I'm calling C, which goes from some small interval, minus epsilon, into the set C. So the curve lies in this set, and at 0, the parameter is 0, it gives me X, its parameter lies by T, and then, but it's derivative. There's a derivative vector to this curve. Now, as I say, some people at that point would want to normalize that vector to make it be length 1, but I'm not thinking that it could be anything. In fact, I'm including in here the vector W equals 0. How could that be? Because you could easily construct, I don't know, constant curve. It just constantly at this X. It doesn't do anything other than stay at X, and then the derivative would be 0. So anyway, I look at all those vectors, and it's part of the character of whatever this is, the smooth manifold, that you get a subspace. And then if every subspace has its orthogonal complement, and that's the normal space. But again, you can also think of these are floating vectors. And so you can also think, for example, if this is a curve, there's a tangent line and a normal line at this point. And this is a kind of duality because, of course, if you know the normal space, then you also know the tangent space through orthogonality. Each of these spaces determines another. This is a beautiful principle which we want to maintain as we go further. Another characteristic of this old subject is that you have this geometry. This is kind of something smooth. And this is indicated by the fact that if you think of X moving around in this set C, then these subspaces would move in some continuous way too. Well, what does it mean for a subspace to move in a continuous manner? This is going to get us into set convergence again later. So, but anyway, this is the classical background that we all already understand, but we need it here as a reference point. Now, this was changed in convex geometry because you were given sets that were corresponded essentially to systems of linear inequalities instead of equations. And but in the early days of convex geometry and optimization, polyhedral sets were also very important, which have faces and edges and flat sides. There's something not smooth about them. Those are non-smooth boundaries to polyhedral sets. So essential already immediately is dealing with things where things aren't going to move smoothly around necessarily. So I'm thinking of a question. I'm thinking of a general closed set, convex set, and I'm thinking about how to imagine tangent and normal vectors to such a set, which many of you already know through convex analysis, but to compare it here, there's something more simple that you can do to start with. So the tangent vector, so of course, immediately you also have to generalize the word, because in the word tangent is usually seems to mean touching, but here we mean it more generally because, look, it goes right into the set in my picture. I look at a vector that points right from X into the set, so it's not exactly, well, it's touching. Sure, it goes in, it's touching very much because it goes into the interior of the set. Right, so the way you can do this in the convex case is you start by looking at vectors that give you some way of entering the set linearly. So I can first look at the vectors W here, such that if I move from X in the direction of W, which is to go to a vector X plus tau W, as you see here in the set C, for some tau and some small interval, it's not minus epsilon to plus epsilon now, it's 0 to plus epsilon. I will get a number of vectors by looking at that condition. But that isn't enough because that set of vectors won't be closed necessarily. In this picture, for example, I can get vectors as are shown here, and they can lean more and more over, but in the end, because of this curvature, the limit vector would not be a vector in which I can enter the set C. Along the limit curve, I would immediately leave. So I have to take the closure. So this is the way we would define the sets of these things as in convex analysis, and we can think of them as variations that are feasible, ways that you can be faithful to the set C when you make a variation. And then we can use, we can define normal vectors in a way that at first seems a little different. We look at the vectors V here, such that there's an optimality condition here. If I look at the linear function that corresponds to this V, then the value at X maximizes over this whole set. So I have here a linear function, and it has level sets, which are parallel to this line here. And this is a maximization condition. But it's not hard to see that this obviously is the same as saying that this inner product is less than or equal to 0, and this is an angle condition. This says in terms of angles, the angle between this vector and this difference vector. If I think of a point here, x prime, then this is a difference vector. So it says that the angle between these is obtuse. It's 90 degrees or greater. But again, we allow V equals 0. V equals 0 fits this picture of the definition. And here then we have a relation of polarity. That is, these are the things that are orthogonal to each other. And that's what I'm going to put in here. Okay, now let's remember that beyond a subspace, we have a thing called a cone. A cone is a much more primitive object. It's something which I insist must contain 0. Some people don't do that. It must contain 0, and it should have the property that it contains all non-negative multiples of every vector that's in it, which means that it's a bundle of rays coming from the origin. And then if you have such a cone, you can define its polar. This is convex analysis as a set of vectors which make this condition. All the vectors V that have an obtuse angle or more to the vector W, except also the vector 0 is allowed here as an honorary vector in this condition. And the miracle of elementary convex duality is that if this is a closed that this polar is a closed convex cone, and if you take its polar, you get the closed convex hull of the original cone. Now, there's a special case. This covers orthogonality. So when the cones or subspaces are special cases of convex cones, and then you get orthogonality. So by the way, I was very interested in my, when I was still a graduate student, I got interested in the whole concept of duality and optimization and how to generalize duality. I had somebody told me something that changed my life. He said, well, I was very fascinated with linear programming duality. And he said, but nobody knows about what to have for nonlinear programming duality. So that became a huge inspiration to me. And I at an early stage where I was working on my doctoral thesis, I created a kind of a duality theory, all revolving around polar cones and all the things you could do with them. But then I discovered in a book of somebody, conjugate convex functions of Fenchel, and then I had to revise all that by the time I made my thesis. But this is the seed, the basic core of everything about duality is this polarity of cones. So now the beautiful fact in convex analysis is that the classical orthogonality between the normal and the tangent spaces is replaced by this kind of polarity. So when you have a convex, according to those definitions I gave, we get the tangent cone and the normal cone are both closed convex cones, and they're polar to each other. They satisfy this formula, and we see it in this kind of picture. If you want to look at the normals, they're exactly the vectors that make, here we have like a right angle. These are exactly the vectors that make a right angle or more with the tangent vectors and correspondingly. And this is so fascinating to me that when I went on to try to generalize this later, working with my student Francis Clark, I insisted that we should have this polarity, but in some ways it was a bit of a mistake, as I will explain later. All right. Now we're going beyond convexity, as you can see by my monster that I put here. So I have a set C, which imagine it to be, well, 1,000,000 dimensions is too much, but you can imagine it to be 3-dimensional. And now I want to say, what am I going? I want a concept of a tangent vector, and I want a concept of a normal vector, or maybe more than one concept. But here's what doesn't work. I can't define tangent vectors just starting by using line segments that enter this set, because, for example, I'm trying to show here a cusp. There's no line segment here that enters. Every line segment will immediately leave this set. So I can't use line segment, at least at this point I couldn't. But even at these points, there are various points I couldn't use just line segments. And I can't define normal, and then also tangent. So what do I mean by tangent? Here, look at this point. So I try to draw a really interesting point here. So on one side here, we have an infinite sequence of little solid balls, let's say, tiny, tiny balls, infinite sequence that converges to this point. And on the other side, we have hollow bubbles inside the set converging to this point. Is there something like, well, okay, I suppose up and down here there are tangents, but what about this? Is there a tangent out in this direction to this set? So these are constant difficulties you have to understand, or, well, why do you want to deal with this set? Who's interested in this set? Is this going to be the feasible set of some nonlinear programming problem? Well, conceivably we could set it up that way, but it would at least have to have infinitely many constraints. Well, I don't know. But it's not so much for that. It's the fact that once we get started in this direction, we're not just going to deal with feasible sets and defined by constraints. We might be dealing with all kinds of other sets derived in many, many ways. So we don't want to put an obstacle in our way. We want to do this with complete generality, although we can assume closedness. That is really a very simple thing to assume and make do it. So what might be our guideline? So we can go to what people did in the early days of optimization with nonlinear programming. They looked again, like in classical differential geometry, they looked at curves based on some little interval that enter the set. So the whole curve is in the set C, and it starts at X and has this derivative W. So those vectors W, well, these are what are called derivable vectors, derivable tangent vectors, but they're not good enough. You're not going to get any derivable tangent vector out of this. There's not going to be any curve that goes over, or also there are problems in this direction. This is curves. Continuous curves aren't going to do it. We'll have to use something more. So even though this works for a lot of good sets, convex sets, smooth manifolds, nice sets defined by constraints, it's not going to work for general purposes. So we have to look at things in a general way. So here we're going to look at tangent cones. We'll get from directional convergence. I have a little picture here to show you what I mean by directional convergence. It's very intuitive, really. So I have a sequence of points here that approaches. The picture should them getting smaller and smaller, like infinitesimally close. There are infinitely many points approaching here, and you see they do it from a certain direction. How do we understand that direction? The direction is that we can look at these difference vectors and then normalize them so that they don't go off to infinity. These difference vectors, and anyway, the angles of them, somehow we can get, by scaling, we can get them to converge to W. So that's what this expression shows up here, some kind of scaling. So now if we look at we're going to define the tangent cone by looking at all the vectors we could get by simply from sequences, not curves in the set. And then that will give us, there's a rather nice point shown in this picture, but that will give us, all those vectors W will give us what we will call the tangent cone. But that's just the general tangent cone. There's also going to be now a regular tangent cone. There's a different kind of duality that's going to enter in the subject with the general and the regular. And this is something which is goes back to Clark But this demands some sort of local stability. It's usually not defined this way. It's defined by some more complicated, okay, no, here's the limit that defines it, but this limit isn't very intuitive. But it has a special characterization in terms of set convergence. I put this in quotes because I haven't explained set convergence later, but intuitively what this means is the following. These vectors W are the vectors that they're tangent vectors, but at all nearby points of this, here's at X, but at all nearby points, there's a vector that gets close to this. So no matter how close I am to this X at a different X, X nu, I can approach this vector. So this is a concept of tangency that demands a kind of stability. And it leads to a surprising fact, which will come out in a moment, which was extremely motivating for this otherwise strange looking definition. Let's get to normal vectors. So again, we have general ones and normal ones. I'm using a hat for the regular ones, right? Because that's fancier. You wear a hat and you're a higher class person. So this is at least used to be that way. This is the normal cone, regular normal cone, and it's defined as follows. Now, you remember the definition that we had in convex analysis, which was some kind of like a maximization. And here we have this, but there's a little error term. And the things that satisfy the same kind of condition as in convex analysis, but with a letter error term, those are going to be the ones that are in this cone. And here you have a picture. So for example, this vector, you need an error term because of the curvature going in this way here. This vector will satisfy that it was error term. Anyway, that gives you this, what's called the regular normal cone. And then we get the general normal cone, which is obtained by absorbing nearby information, which we have where we take limits. So we look at all of the things. We look at all the nearby points, and all the normals there, and then all the things that we could get and take limits. And this, in set terms, this is what will be called an outer set limit, and it's given by this kind of lim sup. So we have for the tangent cones, we got a lim inf, and for this we have a lim sup. Now, there's an awful lot of hard work that went into getting these definitions where nobody really knew at the beginning what to do correctly. And it was explored from many directions. So as I say, the regular tangent cone was the tangent cone that was developed by Clark. And you'll see why in just a moment. And based on that, well, okay, but maybe I have to go to the next slide before I can explain this a little more. But what the normal cone that we ended up using, and Clark and I, when we were working on this theory originally, was we would take all these limits, but then we would take the convex hull. And that was based on or at least my passion for making sure that the cones would be polar. Well, let me go on to the next slide because this will explain something more. So we go to the fundamental tangent and normal relations in variational analysis. And you see I have my tangent cone, two tangent cones, two normal cones, and the ones with hats are the regular guys, or the higher class ones, which and then we have the central relationship. So first of all, the regular one is a subset of the general one, and the regular one is convex. That's the bombshell about the Clark tangent cone. Now being in this context being called the regular tangent cone, that strange definition makes it be convex. It's a convex cone, and both of the cones are convex, with this one being a convex subcone of that one. But then on this other side, we have the normal cone. So the normal cone, regular one is included in the general normal cone, and the regular one is convex, and both of these cones are again closed. But then even more dramatically, we get this double polarity. So the regular cone is the polar of the general cone. And but remember, it's not true that both cones are convex, only the regular ones go. So this is taking the polar of a non-convex cone. I get this regular normal cone, and whereas the regular tangent cone is the polar of the general normal cone. And moreover, and maybe this follows from that, the two tangent cones are equal even only if and only if the two normal cones are equal. That is the case that is variational regularity. And it holds for lots of sets that are of great importance. Convex sets, smooth manifolds, nice feasible sets of nonlinear programmings, but it doesn't hold for all sets, and that's necessary. For example, that we will look at sets that are the graphs of subdifferential mappings of convex functions. It won't hold for such sets, but we need to use this geometry for such sets. And the interesting thing about it is that this fundamental fact about the geometry of a general closed set was unknown in all the history of mathematics until variational analysis. Now, as I explained Clark was working with the tangent side of this, and he was, and then so this condition that the two tangent cones would be equal, he called this regularity. So, and I called it in the variational analysis book, Clark regularity. But Mordovich at a later date started working just with the normal cones. And at first I was resistant to some of Boris Mordovich's ideas because it's a little hard to explain here, but it has to do with something I call horizon subgradients and how they're needed in calculus. And it seemed to me something was missing because what he did was he did not take the convex hull. You see, now suppose we take the convex hull. Okay, okay, here's what I mean. So if I want now the polar of this, I have to go back to the double polar of that, and that's the closed convex hull of this. So if we take this as the main important object, then we want to have the closed convex hull of this. But this turns out to be bad for the calculus. And I remember very distinctly, although I heard Boris Mordovich explain these ideas, I remember a time back, I think it was 1986, late 80s, I think, 1980s, after he had emigrated to the United States from Russia. He had a book in which there was some result, maybe I'll be able to explain it later, but anyway, it convinced me that we should not take the convex hull. We should not pass to the bipolar of this, even though it has some importance in some ways. And then I tried to convince Clark that that was the case, but he resisted. He never wanted to go in that direction. He always wanted to go a different direction. And I don't know, we diverged in our research at that point, which was a bit painful, but that's what happened. So now to go on with the mathematics of it, one of the things you get out of these ideas is it's a very simple thing, but it's just kind of like dramatically interesting to me anyway. That you know whether a point is a boundary point because if and only if there will be a non-zero normal vector there. It's easy to see why that's the case. You see, suppose you take some sequence of points. I call them here. I'm looking at an x bar. I'm looking at an x bar nu that's approaching this x bar, but is outside this set. Then I can look at a point that's closest to the set. If I'm near enough, there will always be some points that are closest. Now, if I look at the difference vector, that difference vector, as we'll see in a moment, will be at least, well, it will be in particular a normal vector. And then as this moves over to here, this will move there, and then those vectors, if you scale them, for example, to length 1, they would approach something, some cluster point would be a normal vector. So you have this beautiful little characterization. And to put it another way, you know that a point is in the interior set of the set if and only if the only normal vector is the zero normal vector. The normal cone is the zero cone when you're in there. or it means the regular tangent cone is the whole space. All right, now here's another, to me, very beautiful point, and it also illustrates a little way of divergence where Francis Clark and I were thinking differently. So in Clark's original work, the main emphasis was on proximal normal vectors, which are a second order kind of a condition. They have to do with the kind of projections I just showed you in a picture. But here's a full characterization of general tangents of the regular normal, regular normals, which is very beautiful. And well, it's very easy derivation, but just let me say, it comes out, because I don't want to take too much time here, I still have a lot to say, that the vectors that are the regular normal vectors are exactly the vectors such that there is a function h, a smooth function h, a C1 function h, which has its maximum at this point, and v is its gradient. So this is the cone. This is exactly the cone of all the possible gradients you could get by looking at differentiable functions that are maximized at this point. So in other words, it shows that the concept of a regular subgradient has a very fundamental meaning for optimization theory. A very fundamental concept at the very base of the theory of optimization. A normal. Okay, so they are so beautiful. They're so important in optimization. Well, why then do we need the other ones? Well, we need the other ones, for example, for this boundary and interior condition, but for much more, it's for the calculus. So now let's get into optimality conditions. How does this help us in optimization, or give us a new way, a new angle on the whole subject of optimality conditions? So, from that little characterization I just gave, you could go further and say that there is that if you had that was a maximization condition. Let's turn it into a minimization condition. You can say that if you have a continuously differentiable function f0 that has a local minimum at this point c x bar relative to c, then the minus the gradient of that function belongs to the normal cone. For the maximization, it was the gradient of the function being maximized. For minimization, it's minus the gradient belongs to that. It's in the regular normal cone. Now, since the regular normal cone is inside the general normal cone, then this says also this must be in the normal cone. Now, of course, if I have a case of variational regularity, the two cones are the same, so it doesn't matter. Otherwise, it looks like this is a stronger condition. So now we come again to a very important idea, because so much of the history of optimality is to try to find the weakest possible necessary condition. And then same with sufficient conditions, why weak is and so forth. But weak isn't necessarily better. But is it useful? What is useful? For something to be useful, you have to have a calculus of it, so that you can apply it in the case of structure. We don't, we know about how many times do we check deltas and epsilons when we're doing differentiability? No, we use rules of calculus, chain rules and so forth. We need a calculus to make use of a concept, and for the general normals are much better for this than the regular normals. And in fact, they are much better than what would be the normals we would get if we had taken the, I don't want the, if I took, it's also true that this would belong to the closed convex hull of that, and that would be the normal cone that was in the earlier theory that Clark and I were working on, but we don't want that. This will be a better calculus, and the reason it's a better calculus has to do with fundamental contributions that Mordahovich made to that subject. All right, so here's an example of a kind of, and actually this is an example of the very formula that was in the book of Mordahovich, which convinced me that we had to abandon taking the convex hull of those vectors. So I'm looking at the case of a set which is the intersection of a finite collection of closed sets. And I'm looking at a point now, we need in all of this calculus things like constraint qualifications usually come in. We know these constraint qualifications from optimization theory with constraints, and here there aren't exactly constraints, but it's very, very similar. It's some kind of condition that's not very serious, but still needs attention. So, but has an interesting form. So we're looking at this, and we have all these different normal cones, and we look at the possibility of selecting a normal vector from each of those cones, and can you do it so that they add up to 0? And the condition is that this should only be if the vectors are all 0. So you see here something actually which is very similar to something like linear independence. It's a kind of thing of that character, which, as I remember when I first studied linear algebra, was a very mysterious kind of condition, because it says there should not be such a thing. It's kind of and many of you maybe teach things like linear algebra. It's something that students struggle with a lot in the logical organization of such a concept. But anyway, we have it all through this theory. Here is a constraint qualification. Then we have that the normal cone at the set C is included in the sum of the normal cones. So here again, we go beyond classical thinking a lot, because we're using the sum of sets. So the sum of sets is all possible sums of vectors selected from the sets. But in general, we just have an equation, an inequality here, an inclusion. However, if all of these sets are variationally regular at this point, then this is an equation. But there's something more, something even grander about it. Not only is it an equation, but then you have determined that the set C itself, this intersection, is this regularity. So this kind of result not only gives you a calculus of the normal cones, but it gives you a calculus of this kind of regularity, which you can carry on and on through many steps, as we do in our work in classical calculus. And here now then is how you could connect it up with Lagrange multipliers. So let's consider now that we have a set C, but look at it in a very general way and to begin with. I have a set C, which is given in terms of, I have a collection of functions, M functions here. And I look at this vector of functions in the space Rm, and I want that vector to belong to a set D. And these are all C1 functions. When will this vector belong to a set D? And a typical case of nonlinear programming is a case where the set D is a very special kind of convex cone. It's a product of intervals. In general, I like to think of a set that's a product of intervals. I call it a box. Here's a very special box. It's the product of these intervals with some intervals that just reduce to single points, the 0 intervals. And that would mean that, so F1 has to be, and there's F1 of x is less or equal 0, F2. So this is very general, but this could be some kind of ball, or it could be some other general cone. We have Lorentz cones. There's so very many versions in optimization of what kind of cone this could be, called cone programming if this is some general convex cone. And even if you could turn this into matrices, because it's positive semi-definite programming. So this is a very general kind of model with this as a special case. Then we can think of multiplier vectors. And these multiplier vectors are associated with this. And in this nonlinear programming case, there's a multiplier vector for each of these components here. But in general, for this D, what are they multiplying? The multiplier idea isn't necessarily good. We should maybe just call it a dual vector. They aren't multiplying necessarily. But anyway, so I'm looking at a vector there, and then there is a constraint qualification, and this constraint qualification in this format where the general closed, well, it could be any it doesn't have to be convex even. And what I'm talking about right now, this could be any closed set, not necessarily cone, not necessarily convex. And still we have this formula. So this is like the kind of triumphs of these theories, that you can work with this generality, at this generality of any kind of closed set here. All right, and here is the constraint qualification. It has the same character. Instead of, okay. So the constraint qualifications involves vectors that are in the normal cone to the set D. So I need to then calculate this. This is where more calculus would come into play. What if this D is a box? What about this special case? Then whatever that is, that will give me a formula, maybe with even more work for this normal cone. Anyway, the condition is that that there should not be any vector in that cone which gives me a linear combination equal to 0. Again, you see the similarity with linear independence here. Something like linear independence of these gradient vectors, but with the coefficients restricted to some other normal cone. And then under that constraint qualification, we have a formula. And it's more general, and I could give it as an inequality, but for the purpose of this talk, I'm going to state this by assuming that the set D that's in this picture, at my particular x bar, I have a vector that will belong to that set D, and at that D, at that point, I want that set to be regular. So it's regular normal cone and it's general normal cone coincide. And an example would be that this D is a convex set, like a convex cone, like this classical case. Then, by the way, this would, in the classical case of this set, this would reduce to the classical constraint qualification in nonlinear programming. Mangasarian Fromovitz constraint qualification and so forth. Anyway, the conclusion of all of this then is that the set C, well, there is a formula. First of all, there's a formula for the normal cone. That the vectors in the normal cone are exactly the vectors V that you can represent as a linear combination of the gradients under the restriction that the coefficient vectors you use are the ones to belong to this normal cone to the set D. And then there's the bonus of all this, that it also shows that then the set C is variationally regular. So if we think about this in this particular case described of a nonlinear programming problem, I have this constraint cone given by inequalities and equations. And it's possible, I won't write it, I can't write it down here. I could just we all know what the conditions should be on the norm, on the multiplier vectors. For the equation constraints, they can be arbitrary multipliers, but for the inequality constraints, they're the complementary slackness condition that comes in. And that turns out that is exactly the condition that Y belongs to this normal cone for that particular choice of the normal cone. And anyway, then we have this turns out to be a classical constraint qualification in linear programming. So then by this theorem, we also have, not only do we get this formula, which I can say more about in a moment, but we get that the set is variationally regular. So this is an example of sets, feasible sets of nonlinear programming, which have this beautiful double dual irregularity property of variational geometry. Right now, what good was this? Why is this connected with Lagrange multipliers? Go back here, because you remember, oops, this one here, because I'm working with this basic condition that minus this vector should belong to this normal cone. So now, if I have a formula for this normal cone, I can put in there that formula and get more detail. So as you can see now, if we go back to this, I put that into that. What I will see is that this vector V now is minus the gradient of F0 at X bar. So minus that gradient is equal to this with some special Y bars. And so this becomes a Lagrange multiplier rule. Now let's reflect on this a moment. What's important about this? This is a derivation of a classical Lagrange multiplier view. But we already know how to define it. There's nothing new about the classical Lagrange multiplier view in nonlinear programming. So what is added here by variational analysis to this? It's not that it's added, anything is added to it, although this variational regularity is added to it. It's a property of the feasible set. But what's important is it shows that all that thinking that goes into deriving optimality conditions, that you can see it as part of a much bigger picture. It's part of variational analysis, where then you develop more and more special formulas for the particular kinds of sets C that you might be encountered in optimization. It's the fact that we reduce all of the special thing to something far more general, a calculus, a kind of geometric calculus. So what is the prospect of all this then? A prospect is this great generality. Even though we start out by looking at one-sided effects of constraints, this variational geometry covers all closed sets regardless of any structure. But it doesn't end there. That's, a lot of things in pure mathematics can kind of end at that level. So we have the normal cone and the tangent cone. But the key part of it is that this variational geometry goes together with a calculus of all these things, a calculus of how the special way that you might express the set C leads to estimates, if not exact formulas, for what the normal vectors are to see, what the tangent vectors are to see. And that's how it can be applied. You can't apply such a special theory unless you have the means to connect it to the special features of your subject. That's the beauty of classical calculus. As we know, the rules of calculus lead to so much. You don't have to know much about the function in order to articulate the rule of calculus, but then in a given problem, you have to know how to differentiate things. So then, of course, as I say, it applies to general sets. Well, what sets might you like to look at? So far, I've just been really looking at feasible sets, but we could look at them on other things, and this is going to come up as we go together, go ahead in this lecture. So, for example, we could look at the epigraphs of functions. Epigraphs of functions are going to be closed sets. Functions on Rn gives closed sets in Rn plus 1. And we saw yesterday that even in convex analysis, we need to work with epigraphs of functions, not with graphs. And then that's some kind of general closed set. So that kind of set has the two kinds of tangent cones, the two kinds of normal cones, and those lead to some kind of concept. So the tangent cones lead to some kind of subderivatives. The normal cones lead to some kind of subgradients of different kinds. And then all of that can fit together. And then the relation, the duality between the tangents and normals must lead inevitably to some sort of duality between subderivatives and subgradients. It's so beautiful and thrilling, really, that once you understand something on a very, very fundamental level, like this variational geometry for arbitrary closed sets, it's an engine that can carry you everywhere in outer space. So, okay, there are the epigraphs of extended real valued functions, but what about the graphs of set valued functions? We saw yesterday that set valued functions are very important, and you can just imagine them as having arbitrary graphs in a product space. So now we imagine them as a product in the product space of Rn cross Rm, for example, so finite dimensional space, and it could be a closed set. That's a special simple property, a closed mapping. Its graph is a closed set. And then we could look at normal cones and tangent cones to that, and the two kinds. And there must be a kind of duality to that. So what could this all mean? So this is something that has been explored and is understood quite beautifully now. So with the set valued mappings, you get some sort of derivative, graphical derivatives, regular and general. And then with the normal cones, you get something called co-derivatives, regular, normal. The co-derivatives are something that were a mainstay of the work of Boris Morgenowitz, contributing to the subject. And the thing is, once you look at the graphs of set-valued mappings, you don't have regularity in general. So this is the case with a subgradient mapping. The graph of a subgradient mapping is almost not really going to be regular, except at very special points. Variational regularity fails. So you really need both kinds if you're going to deal with things like subgradient mappings. But why do you want to deal with subgradient mappings? Well, this is also a form of second-order differentiation. If you have the subgradient mapping, which is in a certain way a first derivative of your function, and what if you can differentiate that? What would that mean, and how useful it is? It is useful. It is useful and very useful. And this gets us into second-order variational geometry. So we look at a set C, and it might have curvature. Oh, so the classical one of the things that characterizes nonlinear programming and polyhedral sets is you're dealing with sets that essentially have no curvature. Everything is either flat or pointed. There's nothing to be called curvature. But how could you describe a curvature of a set? So of course, you look back at my pictures. I certainly have sets here that are shown in these pictures, which are curved, and they have normals. Now, what can you do about how the first order objects allowed us to introduce, we're looking at tangent vectors and normal vectors, and but how do you capture a curvature with that? So here's what you might think. You might think, and there's something to this. What you should now do is, this is the tangent and normal cones we have are somehow first order. Maybe there should be something like a second order tangent cone, a second order normal cone, whatever that could be. And there is, in fact, a theory of second order tangent cones, but it doesn't quite have the vitality that you might think it might have. It's useful, it's important in its way. But the problem is that the curvature is a quantified thing. You want to give a number to the curvature. Whatever it is, how are you going to get a number to it? So here's the secret of how that finally comes out. Instead of looking, this is getting ahead of ourselves, but some of you will follow what I'm saying. Instead of just looking geometrically at the set, I have to pass to the indicator function of this set. And then from the indicator function of this set, I can get a generalized second derivative. And how am I going to get all that? Well, that's why I just need all this theory here. I have to be able to look at these set-valued mappings and so forth. So in particular, in that case, when you're dealing with integrator function, you're actually dealing with the normal cone mapping. This is a set-valued mapping which takes a point and assigns, if it's a point in the set C, it assigns the normal cone. If it's a point not in the set C, it assigns the empty set. And this is a certain set-valued mapping that has a closed graph. And then you could differentiate that. And by differentiate that, actually you get something corresponding to a generalized second derivative function of the indicator function. So this is getting ahead of ourselves, but it just to show how once you get a firm foundation for the basic variational geometry of tangent and normal vectors, there are endless things that you can do beyond that. So I seem to be ending a little early. Maybe I talk too fast, but what I've got here is something which is not so much meant to be read aloud, but to be looked at by somebody who goes back to this lecture. But instead of reading it out loud, let me just say what it's about. So I first of all want to point out something about the book Convex Analysis. Of course, I wrote this book so long ago. I actually finished this book essentially by the end of 1967 or the beginning of 1968, and it was going to be published in Princeton University Press, but it took forever to get it published because first of all, the first editor got sick and then she died, and then there was a second editor, and then he left for another job, and meanwhile, there were all these delays. So basically, it took over 2 years for the book actually to come into print. And meantime, of course, my ideas were developing more, but once that book was in print, I never had a chance to revise it. But many of the things I'd like to talk about now are not in this book in the way I would like them to be. I'm very proud that this book is one of the most cited books in mathematics. That's just very thrilling, and people are still looking at it, but I wish I had an update of it. For example, you never see the notation for a normal cone is never in this book. What you see instead of the normal cone is the subgradients of the indicator function. Well, it's true that the normal cone is a subgradient indicator function, but something's missing. And then also the tangent cone, and certainly this notation. So all of this is embedded in the theory of subgradients. We look at the directional derivatives of the indicator function, the subgradients, the indicator function, but the simplicity of these polar cones that I try to emphasize here is lost. So in the variational analysis book, in the second chapter, well, even then the tangents and normals aren't in there. But anyway, in the variational analysis book, I'm finally able to put it in the right way, although of course I use this in many papers since convex analysis book was done. And in the main way, place for all this variational analysis, variational geometry that I covered in this lecture is in chapter 6 of the book Convex Variational Analysis, which by the way took 10 years to write. Roger Wetz and I, in fact, after first couple of years or so, we threw out that version and started all over because we had better ideas. And let me just say that in that book, that book is organized in a way to create this whole huge subject consistently, but it's not necessarily the best way to start learning it unless you want to learn the whole subject. So to get as far as the ideas of variational analysis, you could skip rather quickly. You could skip chapters. You could also didn't have chapter 3. You could skip pretty quickly into chapter 6, almost from chapter 1. You could go on to chapter 6. But some ideas that are in chapters 4 and 5 are going to be in my lectures anyway. In the fourth lecture, I'll be describing these things having to do with set convergence and approximation. So that will be the background. All right, that's the end of my lecture for today, and I'll just leave this on the final. I'm in a little early. I hope that's not bad. By the way, to me, a lecture is typically 55 minutes, so I was a little shocked to see that there was a 90-minute window.
Thank you, Terry. No, I don't think you ended early because it's supposed to be 50 minutes.
It is, okay, that's reassuring. Okay.
I
was shocked when I saw that there were 90 minutes. I know some in France, they have lectures that go 2 hours.
But the discussion will can last until 6:30. Yeah.
Okay.
No, you're totally fine.
This question earlier. Yeah, because then I start to think, I have to add more and more to these lectures.
No. Yeah, anything.
Okay, this is good. I'm glad then. All right. That's okay.
No, anything. You will be fine, I think.
Okay. All right.
Yeah. Yeah, we are. I think this forum is quite flexible. You can take your time, and you can, if you want to spend more time, it's okay.
Right.
I think because we have long question time.
Yeah. Okay.
So I wonder if anyone has questions from the participants. They can now type in the question in the chat.
Oh.
And then I can read to you.
Okay.
Could you please give us some suggestions on how to better grasp ideas in convex analysis and what to focus on at the beginning?
Okay, and this is convex analysis. So in these lectures, you'll have to forgive me. I'm taking the point of view that many people listening have know something about convex analysis. So that's a little bit of an unexpected question, and the difficulty with the question is that I imagine that people are going to be looking at my book, Convex Analysis. So the question might be, how should you look at the book Convex Analysis to focus on this? And there I say I have a bit of a handicap because I never had a chance to revise convex analysis, and the way the book is written is old-fashioned, let me just say. But everything is more or less important in that book from the beginning. I might now, if I were doing it differently, I might organize it a little differently, but all these concepts are important. And I think you can, what this lecture should tell you is why it's important and where it's leading. So all of those concepts fit into this bigger picture. But if you take some of the earlier concepts in that book, for example, a relative interior of a convex set, why is that important? It's a tool that's used, hundreds. It's used all the time. These concepts as part of the calculus of things. I have to start thinking. So in the book Convex Analysis, actually, hang on just a minute. I have a copy next to me, and I'll look at it. Will help me focus a little better.
Mm-hmm.
Yeah, so the way it's organized, it first just describes what convex sets and functions are, and cones, that's fundamental. And how you add sets together, and all this is fundamental. And then the relative interiors, and then the things about convex. These are just extremely fundamental properties which can't be ignored. But later, I suppose there are some parts one could skip. Duality is my favorite subject, but after support functions, it's possible, I suppose, to skip a lot of things into dual operations. And I would say that much of chapter 4, part 4, could be skipped to go on to chapter 5, and then to go on to the beginning of chapter 6. I think that would be the most fundamental thing to do. I hope that helps answer your question.
Oh, there's another message. You said this lecture series won't cover numericals, but have you seen or met any practical numerical implementations that use variation analysis for optimization?
Yes, absolutely, absolutely. So let's see what to say. You mean, and not just convex analysis, but variational analysis.
Yes, yes, for
I
variation.
am. Well, let me just say this is one of the things I'm most interested in right at the moment. It doesn't mean that it hasn't been used earlier. I have to think a little more about what earlier. But right now, I'm working on augmented Lagrangian methods, and in augmented Lagrangian methods, you are dealing with, and they're not just for nonlinear programming problems or for even more general problems. Nonlinear programming problems they're the questions of sufficient conditions and how to do all these iterations. And I have a couple of recent papers on this very subject. If you look at my website, there are at least 2 papers from just the last year or 2 on augmented Lagrangians, which very, very heavily use variational analysis, and these are papers that even they go very deeply into numerical methods, at least the augmented Lagrangian methods with rates of convergence and all kinds of things like that. So it isn't as if you're just going to look at this general definition and use it. It's a little bit like saying the following. Are there any applications in which the concepts of calculus are important in numerical analysis? Yes, of course, because numerical analysis involves differentiating and everything like that. You know, for example, numerical methods in optimization typically involve optimality conditions. Well, how are we going to derive these optimality conditions in beyond convexity? So very much involved at the very least in the statement of optimality conditions. But optimality conditions are also the basis that people use for inventing methods, algorithms for determining a solution.
So in your papers, Lagrange augmented Lagrange, is it for the nonlinear programming or for the general problem with a set?
It's for my papers on augmented Lagrangians are for even more general. So in this talk, let's see, this talk, just a little bit there, I have these.
Yeah. So this
I'm looking at constraints like this.
But
actually, I'm looking at augmented Lagrangian methods for even something more, where instead of an indicator, so you could say this is a case where, go back even further here, I'm looking at this case where I'm minimizing a function over a set C. So this is a sum of this, but it's there could be some composite structure in here. Instead of just having a set C, I add to this F0 not just the indicator of a set C, but some other kind of function, which has composite structure. So for example, instead of just the indicator of this set C, I could have a penalty representation of this, or many other kinds of things. So anyway, that's the general format in which I end up with a Lagrangian and an augmented Lagrangian. And then there's a question of whether in that, and it's not convex necessarily, there would be the convex subcase of it, but in general, this is not convex optimization. And then there's a question of articulating the augmented Lagrangian methods to work in that way. And the first augmented Lagrangian methods actually were in classical non-linear programming with equation constraints, as developed by Powell and Histones. And there they showed that you could use an augmented Lagrangian method to calculate a solution if you're near enough to a solution that satisfies the strong second order optimality conditions in that subject. And so then what are you going to do in this more general case? You have to develop what the corresponding strong second order optimality conditions should be. And that's where variational analysis comes in very heavily, absolutely, to get these conditions. And then the interesting thing there is I was able to show that I can identify this with a kind of local duality. This involves a concept I call variational convexity. All this is just my most recent research, but of course there's a long history of using these things in many subjects. Then there's a proximal point algorithm, and there are things like that. So, well, there are so many things that involve this variational analysis, without which you could not get anywhere.
Yeah, thank you. I think
Jane, if you're interested in that paper, you look on my website. It's one of my latest papers, augmented Lagrangians and methods.
Yeah, that's great. There are two more questions. One says, I found duality in many forms, such as for sets, for functions, for optimization problems. Is there anything in common that is important to the idea of duality? How to find more useful form of duality?
Yes, Now, this is a question that goes right to my heart. This is exactly what I loved. When I first entered duality, I wondered, how is this all related? I think it's all related. It's all related. Of course, the earlier duality is even just in a duality between lines and planes. There's a lot of duality that goes beyond just optimization. But the duality and optimization all comes back to convex analysis and the theory of conjugate convex functions. All of it. Although you could also express it in terms of polar cones ultimately if you wanted to. But it is all the same duality. It all comes and in a sense, it's been part of my life work to show that all this duality comes from the same source. There's all manifestations of the same basic ideas founded in convex analysis.
Is it in the book, the monograph you wrote, the small monograph? You have a book, right, on this duality?
Duality, well, that's only convex duality there. I think the variational analysis book explains it a bit more.
Mm-hmm. Okay.
The duality part of that book, it
Okay.
shows even more. But as far as dual optimization problems are concerned, it has to go well. You have to introduce perturbation variables, and that's explained pretty well in the conjugate, the book on.
Yeah.
I should have listed that. That's infinite dimensional convex analysis, the book on conjugate duality, optimization. But
so you
yeah,
think everything, every duality
all together. Yeah. So Jane, please.
Yeah. There is only the tangent space of smooth manifold in the book. Where is the discussion of the second order tangent set of the general smooth manifold?
Well, the second order tangents, they have a role in the book Variational Analysis book in chapter 13. You can find them in chapter 13, and they're described there for general sets, but not especially for a smooth manifold. And as I say, I have limited love of second order tangents. They're important for some kind of purpose as a tool, but it's not really a very fundamental concept. I think that the main concept you want to look at has to do more with the kinds of derivatives of set valued mappings, as I've described, and I will be describing it a little more later. But this is the second order tangents are a bit of a dead end idea, let me just say. And I'm not dead, although some people use them. Good friends of mine make good use of them, but to me, they're a small idea as part of a bigger subject. But they are in the variational analysis book in chapter 13.
Mm-hmm.
Any more questions coming?
Not from the audience, not from the participants. I'm reading the chat. See if I skip anything. No.
Okay.
Terry, can you show us the picture again where you have a lot of bubbles?
Yes.
Quite beginning, I was did not understand quite.
Bubble set.
So what's these are? These are balls. Are these balls?
Well,
3 dimensions.
Okay, my idea is here, these are solid balls in some sort of infinite sequence, tinier and tinier, converging to this point.
Okay.
Inside the set, these are bubbles
Bubbles? Like
Bubbles
open,
converging to this
like
point.
the hole,
These
right?
are solid balls outside that are converging.
And what about these? Are they holes?
These are holes.
Okay, so
But
those
these
are
are
holes.
solid. But then the question is, at this point, is there something like a tangent? According to the definition, there is. I can find a sequence of vectors in these points, a sequence that comes to this point from some direction, and then that direction will give me a tangent vector. And you can imagine that these bubbles fit into a kind of a trumpet, some kind of pattern. Maybe I could get a cone of tangent vectors at this point out of this bubble, but there would still be tangent vectors also in this direction. And there would be tangent vectors in all these directions, even though the bubbles are here, I would still have tangent vectors, I guess, in every possible direction here. So the tangent cone in this case would consist of some half space, everything in that way, and then some kind of directions having to do with the way these little approach this point. So I'd have a non-convex tangent cone there. That's good. I'm glad you asked me about that to illustrate that. So at this here, it's much simpler. I would have the tangent cone is going to be a single ray.
Yeah.
And at these points, what about this point? At this point, the tangent cone will consist of a half space, something almost but also an additional ray that goes in this direction.
What's this? Are they belong to the set?
Yes.
Oh, okay.
Little hairs. This monster has hairs. Sure, those are part of the set.
Okay. So the set ends, right? Not like a manifold. It ends up here.
That's right. This is just a compact set with a boundary. It's important that this is all boundary.
Three-dimensional.
Three-dimensional.
Three-dimensional space.
Well, it could be two-dimensional, but I like to think of it as three-dimensional. Okay, so it's two-dimensional. These are just disks, little disks.
Yeah, okay, I see. Okay.
Could be two-dimensional.
Yeah. Yeah, maybe it's easier to think of them as two-dimensional. So this is a circle disk, right? This is a disk.
Yes, you can think of it that way in 2 dimensions, exactly.
Yeah.
And then, but the thing is that then in this tangent cone now, you could, if you look at this point, at all these points, the idea that you could look at curves, derivable vectors or curves, it will work at almost all the points here. Even at a point like this, could be some curve that goes out along this hair. There could be curves going in and around in here. So little one-sided curves that start from this point. They would give you the vectors, the derivable vectors, and those vectors would actually constitute the tangent cone. And even at this point, okay, there's only the curves could be, I could have the curve that follows this boundary, the curve that follows this boundary, but they both have the same tangents. So a tangent cone would be just a single line here. And then, so everything works here, but not at this point. At this point, things are more difficult. So you cannot have a curve. The tangent vector that could come from points approaching in this direction can create some vectors here, but they can't be found by a curve because there are gaps here. It may seem that this is just an arbitrary idea, but it's actually very fundamental.
So this is not a geometry.
Yeah, it has to do with inner and outer limits of sets. Yeah, because you can remember, so as I say here, what's important for a general tangent cone is you don't have to look at a curve, you only have to look at a sequence. There's another way to think about it. We in classical analysis, we're thinking of a variation as moving in some direction. Even in the calculus of variations, that you move in some direction, or it could be along a curve. But here we're kind of moving, it's kind of backwards. We're moving backwards along a sequence. You have a convergent sequence. It doesn't really correspond to our concept of motion, but there's a direction of variation which we are discovering by looking at a sequence instead of a curve. And that's essential to this generality. And in particular then, in this point, you need that sequence generality in order to make a tangent cone work for that situation. Because you're never going to get the tangent cone here just from derivable vectors. Derivable vectors here will give you, I guess, well, if you close them, you know, maybe there's no cone that goes in the direction of these bubbles exactly, but there would be cones if the bubbles get tinier and tinier. There would be curves that go very near it. So if you took those directions and closed them, then you would get all this out. But you would never be able with those curves to get the tangents that come from this direction. Again, this is not the typical set we expect to encounter in optimization, but if we're going to have a theory, it's very important to have a theory that is robust. You don't want to have a theory where it seems fine this week, and next week you find it doesn't work for you because there's something you didn't anticipate. So it's very, very important that this theory works for every closed set and creates fundamental theorem. Was never before known. The work of all the people trying to figure out the normal cones and the tangent cones and the discovery of the Clark tangent cone that's actually convex. Amazing discovery, but then the discovery that we should not take the closed convex hull. We get a better calculus if we don't. It's just, I think it's just so exciting to me, so beautiful.
Terry.
Yeah.
Ask another question, more technical question.
Okay.
So you introduced the second order tangent sets. That's very important for the study of conic programming, like a semi-definite program.
So again, I didn't quite hear. You introduced, I introduced, somebody introduced.
I think for the study of single order cone, right? Or the semi-definite programming, the single order tangent sets are very complicated.
Okay, semi-definite cone. Yes, all right.
Yeah, because the single order tangent cone is very important, but it's very difficult to compute. Even if you compute a single order tangent set, let's say for SDP cone, you may forget pretty quickly, right? If there's any way to learn how to compute the single order tangent sets.
Oh, you're raising some very important issues. So that's a cone which I think deserves an awful lot more study. But I'm so glad you again said about the second order tangent, because although that's there, I don't think that's really necessarily what should be studied. What should be studied is it'll be in a later lecture, the second order epiderivatives of the indicator of that cone. Because that gives, I don't think anybody's here. It's good that you raised this. There's probably a lot of good work to do in this direction. It's a little, you know, I'm really glad you raised this. And there was an earlier question too about the second order tangent cone, because this is a kind of a thing that happens to us when we think about this. We're thinking about this as variational geometry. And therefore, we should proceed on and on with only geometry, sets, and not go to functions. But my view is to go to the second order analysis, you actually have to pass to functions. But what's important is that you can identify the sets with indicators. But the second order theory is going to depend on the second order properties of the indicator function. And then you might think that if you have a second derivative of an indicator function, it would be another indicator function. But that has turned out to be a mistake. Some people think that, and this is maybe something which is behind the idea that we should have this, that the second order tangent cones should be the important thing. So I'm not saying that it's okay. So I think philosophically, this is just my long-standing experience with this subject, that people should explore the second order, this cone. They should explore this cone using the theory of generalized derivatives of its indicator. I'm not saying that it will be easy to compute, but we have a lot of work in there. So Michael Overton and Jim Burke worked a lot on various optimization problems involving eigenvalues, for example. Eigenvalue functions, the semi-definite cone is even defined in terms of eigenvalues, inequalities with eigenvalue functions. And they worked on these eigenvalue functions from the point of view of variational analysis. Are these variationally regular? No, they're not necessarily. But anyway, they discovered a lot of important things about that. I could maybe find some references of that for you if you don't know about it. But this is, I think this is just where that kind of subject should go. There is a lot of work already there, and there are some calculations, very complicated. It involves a lot of classical algebra to get into that matrix algebra, but it's a beautiful and important subject. You're completely right. This is important. People should work more on that.
Thank you. Yeah.
There's a question from the participant. Can you share us more about your graduate school experience? What do you think contributes to your innovation in convex analysis?
Oh, that's I love this question, of course. We all like to hear about ourselves, but this is what's interesting about this question too, is that what happened to me was something, I had my own individual, what happened to me was something that isn't in a general pattern. And maybe there are a lot of other people that are in situations. Okay, so what happened to me was that I was an undergraduate at Harvard University, and I switched into mathematics finally. I didn't want to be an engineer. I decided to go to mathematics, and it got more and more pure. And by the time I was a senior, I was learning a lot of real analysis, and I did very, very well, but I didn't know I wanted to be a mathematician. Then, without explaining why, there were 2 years when I was not at Harvard University. 1 year I was traveling, and another year I was avoiding the Army, and I could do that by being, it was a sudden development, and I ended up at a different university in my hometown, and somebody there told me about linear programming theory, and I got interested in all that. So at that point, I developed my own idea of what I wanted to work on. I wanted to find out about duality. But then I went back to be a graduate student at Harvard University in the pure mathematics department. There was nobody there that had any interest or knowledge about optimization. I had no advisor who knew anything about what I wanted to do. But I had to study pure mathematics, and I love pure mathematics. And that was 2 years, and I had to pass the exams. And then I was doing my own research. Now, how could it be that I was just doing my own research? Well, that's unusual. Most people do research because some advisor is guiding them and giving them topics. Well, the best advice I had was by that professor, wonderful person at that other university that I was at in my hometown. But he was not he was a statistician. I don't think he could have proved a theorem, but he was a very enthusiastic person about optimization, and that enthusiasm inspired me. And then I just was able to do my own. I just started to play with it. I had idea after idea. I had a very good background. That started it. But then it got to be kind of funny in the end. So then I had a formal advisor. It was Garrett Burkhoff, who was the token applied mathematician in that department, but he was more interested in differential equations and some other things. He had no idea of optimization. He connected me with a friend at MIT who helped me a little bit with optimization. But then I have to tell a funny story if I have this opportunity. So, okay, so I'm writing this dissertation. My advisor doesn't know whether it's good or not, but fortunately, Albert Tucker at Princeton knew about me and what I was doing, and he kept telling my advisor that this was good and I should be allowed to continue. So anyway, then finally there was a time when I written my dissertation and it has to be defended. So you know all about a thesis defense, but thesis defense is different in many countries and even at universities. So the funny thing about the thesis defense at Harvard University is that it all happens on the same day at the end of the year. At the end of the school year, the particular semester, all the theses are defended at the same time, but how are they defended? All the faculty goes into a room and closes the door, and the people who have the theses, the PhD dissertations, they stand outside room with little desks, little podiums, little places like you give a lecture from. They stand outside, there's nobody there. And inside the room, your advisor must defend your thesis. Your advisor must explain your thesis to the other people in the room and defend it. But my advisor really didn't know much about my thesis. So at the end of the meeting, they came out, and some people, like some professor in algebraic topology, came out to try to challenge me, but I was a very naive young person, and I just, I was very confident. Well, this is all correct. This is all beautiful. Anyway, they gave up, and I got my PhD. Okay, that's the end of that story. I'm afraid our window has expired.
Yeah. That's very interesting.
Yeah, I think time is up today. How about?
Yeah. Mm-hmm. Yeah.
Anyway, I look forward to tomorrow. So tomorrow.
Yeah, very good, Terry.
Using this subgradients.
Yeah.
Yeah, thank you, Terry. So in order to be a pioneer, you need to be lonely, right? At the very early stages, right?
Well, it's hard to say. Everybody is different, but in my particular case, I grew up as the only son in the family. Maybe there are a lot of people like that in China. I was the only son. Although I had a social life with a lot of people, in some ways, I also at home, I had a lot of time by myself to look at books, and I was very self-sufficient from an early age with interests, and I wanted to learn languages. I had a lot of interests like that to do. And I love to do research. I like as a personality, I liked being alone and thinking hard. I could sit and think for hours and enjoy it. So that certainly helped.
That's good, actually. We should do more.
Well, most of us have, mathematicians have to do this anyway. It's part of the profession.
That's right. That's good profession for you, right? You.
Yes, but I didn't know it when I finished my undergraduate degrees. I thought I might be a lawyer. I might go into business, and it was some accidental circumstances, but it was the best thing. That's the way life is. You don't know. It's very hard to know. Some people really know what they want to do. It sounded like my story. I knew what I wanted to do. I didn't know until I went back to graduate school.
Yeah, that's good. You don't know it. Otherwise, life is meaningless if you know what you can be, right?
Yes, that's right. You don't know. And anyway, you don't know what's available. How do you know about life? How do you know about what is research? What is good? What is bad? You have people trying to tell you these things all the time, but they don't know about the subjects that are important to you, the things that are important to you. Yeah.
Okay, I think Zhang Jin is trying to stop this session, right? Okay, thank you very much.
Yeah. Okay. Right.
Yeah.
Bye-bye, everybody.
Thanks a lot, Terry.
Yeah,
Okay. Good luck tomorrow.
Thank you, Zhang Jin. Okay, bye-bye.
Yeah, bye.
Bye.